So I'd like to start by thanking the organizers for the invitation. It's great to be here. When I saw the title of the winter school and the speakers, I was horrified, and I think I don't do automorphic forms, I don't do p-adic groups, what I'm going to talk about. So yeah, and then I think maybe I should talk about something related, which is affine Hecke algebras. So I decided to talk about a very important piece in geometric representation theory, which is a realization of the affine Hecke algebra as an equivariant K-theory of so-called Steinberg variety. And so this is a theorem due to Kazhdan-Lusztig. And also some version due to Ginzburg. And then how they use this to prove Deligne-Langlands classification. Of irreducible representations of affine Hecke algebras. Okay, so the plan of these lectures today, we will just discuss some basic properties, like definitions and basic properties of affine Hecke algebras. So tomorrow will be hopefully this, or maybe we'll use some part of the third lecture to explain this isomorphism. And then if time permits, I will give some idea on how this goes. But yeah, we'll see how it goes. Okay, so let me get started. So first I want to just discuss a little bit about convolution algebras. So as you all know, if we start from a finite group G, and then we have a group algebra whose multiplication is induced by the multiplication on G, but we can also view this as functions on G, which I denote like this. Simply, so this is a linear combination of elements in G, and you attach a function which sends x to ax. Okay, and then you have the usual multiplication on this group algebra. You ask, what does it become on this side? I hope you have done it before. And so this you can think of this as G times G, and then so you have two projections, which is just on the first two on the corresponding vectors, and then you have a multiplication map. Okay, so this is which sends G1 and G2 to their product. And now if you have a function here, so you have that f, so you have elements here, so f and g, maybe not g, f and f prime, which are functions on G. So we just say the product here induced by the usual multiplication here is denoted by this. Then f times f prime is nothing but you pull back f via p1 and f prime via p2, and then you integrate along the fiber of M. Okay, so this is M push forward of p1 pullback of f times p2 pullback of f prime. And this product here is like the pointwise multiplication of functions. Okay? Okay, all right. Now if you have a subgroup then instead of, so now if H is a subgroup of G, and then you can consider the induced representation from H to G of the trivial representation. And then you consider the algebra of the endomorphism of this G representation. So this has an algebra structure. And you can just play the same game. So this identifies by a junction property of induction. This is the same as space as home from H representation, from the trivial H representation to the induced representation. And you can identify this whole space as functions on the double coset G by H. Okay. And again, so here you have the composition of endomorphism. It induces a convolution product. It induces a product here, which we'll call convolution product. And this is described in similar terms. So you have, so you start with a function which is on G mod H. And somehow in the middle, you have two copies of it. So, but instead of quotienting both by H, you just quotient by a diagonal copy of H. And then again, by multiplication, this sends to G quotient by H. Okay. And then you can perform the same kinds of computation and write down this convolution product as pulling back functions and then integrate along N. Okay. Okay, so it will be this kind of, okay, wrong direction. Wrong direction again. So it will be this kind of algebras that we'll be interested in, and in particular, Hecke algebra is relevant in the following setting. So we start with a connected reductive group. Define over FQ. And then you can, let's fix a Borel subgroup. Well, I assume the group split. So T, which is a maximal torus. Okay. And then for start, all these data gives you some sort of root datum consisting of the following data. So first of all, you have the character lattice, which I denote by bar X. So this is the space of group homomorphism from T to GM. And then you have co-characters. This is GM to T. And then you have roots and co-roots. Okay. And then the fact we have fixing a Borel, so this tells us which are the positive roots, and so this gives us a choice of positive roots and negative roots. And in particular, determines a set of simple roots in phi+. And then the vowel group. So when I write an F, F stands for finite because we'll have a affine vowel group coming up later on. And so this is the normalizer of T quotient by T. Okay. So in particular, this group acts naturally, let's say have choice about choose this one, the co-character lattice times R. And then it is generated by reflections. So, so this is actually a Coxeter group. With the simple reflections given by just reflection with respect to the simple roots. And I hope everyone knows Coxeter group. So this means this is a group generated. So in other words, WF has the following presentation. So it's generated by elements in S and then subject to relations S times U to some power of MSU equals 1, where MSU belongs to 2, 3, or infinity for S not equal to U in this reflection set. And MSS equals 1. Okay, S squared is equal to 1. So our vowel group have a presentation like this. And now we want to perform the convolution product in this setting. So first of all, so meaning I want to consider the finite group G of FQ, and then consider the double cosets by B of FQ. And by Fourier decomposition, we know that the B double cosets on G is indexed by the finite vowel group. So there's a bijection, natural bijection like this. And so the Hecke algebra, so I write an F because this is the finite Hecke algebra. It's just functions on G of FQ quotient by B of FQ. With value in C. And because of this, you observe as a vector space, this is just the same. It has a basis indexed by elements in the vowel group. And then so you want to understand the algebra structure given by that convolution product. So it's so it's equipped with the, maybe I should say that the Hecke algebra is the space equipped with the convolution product. And so first of all, it has a basis, which is just the characteristic function on each double coset. So I'll write TW to be the characteristic function on B of Q, W of B, Q. Okay. And right. And then you need to compute their product. So I'll just give you the answer. The answer is, so there's a notion of length for Coxeter groups. And in this case, so there are several ways to express this length. So the length of W is so Q to the power of LW is equal to the number of elements in BFQ W Q quotient by BFQ. Okay, and so So you can compute the product. Turns out if the length of the elements, if the length of the product is just the sum of the length, then the convolution of these elements is just equal to what you expected. So if L of WV is equal to L of W plus LV. And then you need to understand how it reduces when in the other direction. And for this, you only need to compute for the simple reflections. And for simple reflection, the relation is Ts plus 1, Ts minus Q is equal to 0. Okay. So I encourage you to do this computation for the case of G equals to SL2, and then, or GL2. So exercise, do the computation. For GL2. And then you will understand this relation, which is the most crucial thing in this business. Okay. So. No, I don't need to give Ts times Tw, because if W times S gets smaller, then by exchange relation, I can always write Tw equals to Tws times Ts. And then I play this relation. Yeah. So this suffices to characterize the algebra. Are there other questions? Yeah, yes. So it's the minimal length of reduced expression. Well, the length of reduced expression is the minimal length of the expressions. Oh, no. Okay, maybe one remark that at this stage, when you describe this algebra this way, you can forget about G and B. It only depends on the group, on the coxeter group W itself. Okay, so you can define this algebra for any coxeter group without talking about the reductive group G or the Borel. Okay, and then there's also there's an equivalent description, which is so equivalently. So HF is an algebra. So it's an C algebra. Yeah, maybe another remark I should mention. So for there, Q is just a number, because Q is like a power of the prime coming in this finite field. But once you get to this presentation, you can just view Q as a formal variable. And then you can specialize Q to whatever you want. So as an algebra, this is generated by Ts, where S belongs to S. And then if you follow the coxeter presentation there, so you have Ts, Tu equals to Tu, Ts. So this is a braid relation. There are MSU terms here and MUS terms here, and these two are equal. And then you just deform the relation S squared equals to 1 to Ts plus 1, Ts minus Q 0. And also you see that if you specialize Q equals to 1, you just get the group algebra of your Val group. Okay. All right. Now we can, this picture generalize to the affine setting. So now let's talk about affine Hecke algebras. So in parallel to what we have discussed about G mod B, so here what you do is you fix a local field K. And with O, the range of integers. And then let's say small k, the residue field. So O mod the maximal ideal in O. And let's say this is a finite field of cardinality Q. Okay. So again I will fix a reductive group which is split over K. So and then if I consider the K points here, so it contains this maximal subgroup G of O, but then I can go to, by applying to the map from O to the residue field, so I get to G of K. And here I had my Borel B of K. And then I take the pre-image of Borel under this map, and this gives me a Iwahari subgroup inside G of O. Okay. And so things are a little bit infinite now, but the idea is basically the same. So you can consider an algebra which is, let's say, locally constant, compactly supported functions on the double cosets of I on GK. Say with values in C. Okay. And equipped with the convolution product. Okay. And so this is basically the affine Hecke algebra that I wrote. It's because this is a version of extended affine Hecke algebra. Okay, so now how is this coset indexed? This is indexed by the so-called extended affine vowel group, which I will discuss in a minute. So this is extended affine vowel group. Okay, so what is the structure of this group? It has two parts. So first of all, it has all the co-characters of your torus T, and then it has the usual finite vowel group inside it. Okay. And so this is maybe let me explain how it acts on the representations. So on this X check R, this is remember this is the co-character of T tensor with R. So here the WF action is just as before. It's generated by reflections. So WF acts action as before. And then this part's acts by translation. So for any gamma belongs to X star of T, the action of, so we will write T gamma, the corresponding element viewed as an element in the extended affine vowel group. The corresponding element. Then its action on a co-weight lambda is just given by lambda plus 1. Okay. And then it's easy to observe that they satisfy the semi-direct product relation, i.e. if you have Wt gamma times W inverse is T of W gamma. Okay. So I want to emphasize that this affine Hecke algebra, it depends on the choice of your group G. Okay, so if G is because this lattice depends on G. Okay, so if G is simply list, for example, let's say SLN, then this co-character lattice identify with the co-root lattice for SLN. So this is spanned by the co-roots. But if G is a joint type, so if it's PGLN, then this will be the co-weight lattice, which contains the co-root lattice. So in the first case, so if simply connected. So in the first case, in this case, then this extended affine vowel group is it's again a Coxeter group. So that is we can add in, so it is generated by the simple reflection before plus another affine reflection, which is usually known by S0. So this set I will denote it by S affine. So it's a simple so meaning that this group, so this group again has a presentation of that type on the top of that board. Okay. So maybe I should give an example. So let's say SL2. So then, like SL2, the torus is rank 1, and then the usual finite group can be thought as doing the reflection corresponding to 0. But now you can add the affine vowel group. For SL2, it's generated not only by reflection with respect to 0, but with respect all these walls corresponds to elements in Q check. Okay, so you can denote so this reflection will denote by S. This is the simple reflection in the finite part, and then let's denote the reflection corresponding to this by S0. Let's say this is S1. Okay, and then you can check that the affine vowel group in this case is equal. It's the Coxeter group generated by S0 and S1, and there's actually no relation among them. So it's only relation S0 square S1 square is equal to 1. So in this case, i.e. n S0 and 1 is infinity. Okay, it's an infinity dihedral group. I haven't defined, so I should. So a affine vowel group is Z of Q check semi-direct product with the finite vowel group. Okay. or you can take it as in the case when the group is simply connected. Then what you get is the affine vowel group. In general, what you will get is a so-called extended affine vowel group. So I'll not go into detail this. So here you see that the difference between this and this is here you get a larger lattice, which is P check. Okay, so in the case of SL2, so this is, maybe I should write SL2. So in case of SL2, this is, so Q check is 2 times Z, because it's Z alpha check, and for PGL2, Q check is just, is Z. Okay, 0 for omega 1. Yeah, maybe you're right, yes. Yeah, thank you. So S0 is I do so I do this, and then I translate by alpha check. Cannot do it in my head. Yeah, I think you're right. So yeah, S0 should be this one. Thanks. Yeah. Okay. All right, and then so the difference of P check quotient by Q check, this is a finite abelian group, and it's denoted by omega. This group, I will not explain how, but this group can be identified with the automorphism of the affine linking diagram. Attached to this affine group, but you can ignore this part. All I want to say is that this group acts on the affine vowel group by automorphism, actually. So we could describe this so this extended affine vowel group is actually just the affine vowel group, but semi-direct product with this finite abelian group, omega. Okay. And if we want to have a Coxeter presentation, Coxeter type presentation of this group, you use the Coxeter presentation for the affine vowel group, and then you have a length function on here, and then you declare elements of omega just has length 0. Okay, so using this length function, we can, so using this length function, I will just write down a lemma of how to compute the length of elements in the affine vowel group, but I think I will not have the time to prove it. So this is a lemma due to Iwahori and Matsumoto. Which says if you take an element in a finite vowel group and a lambda in this co-character lattice, then the length of an element of the form T lambda times W, in the sense we just explained, is the following. So it's a sum of running over positive roots alpha such that the W inverse of alpha is also positive. If your alpha is in this case, then you do the pair between lambda and alpha, you get an integer, and you take the absolute value of that. On the contrary, if you have a positive roots which W inverse makes it negative, then here you do lambda alpha minus 1. Okay. So it's, I mean, it's more important to know this formula than actually proving it. So in particular, you notice that this length function is not additive in lambda. Okay, it depends on how lambda behaves with respect to the roots. So maybe I'll just give our example for PGL2. So for PGL2, if you have, so the length of T, let's say PGL2, let's say the lattice is generated by the fundamental co-weight P on, then the length of M times this. So this is a dominant weight, and therefore we're in this situation. And so this is equals to M. Just a second. So yeah, so here, yeah, whether it's dominant or not dominant, the S is trivial. So so we're always in this situation. But if I have the length of Tm P one check times the simple reflection, then I would always be in this situation, and the length is equal to n minus 1. Okay. And therefore, you can check, for example, here, if you do T bar check 1 times S, this would be an element of length 0. And this has length 0, and our omega is actually 1, the identity element, and this element, like 0 to Z. Okay. Okay. Questions? Okay, so that's the extended affine vowel group. Now I want to explain a presentation for the affine Hecke algebra. Sure.
So in the simplified case, when we have this S0, what is the length of S0 times the word?
Times what?
Times an element, times an arbitrary element.
S0 has length 1. It's a generator of the Coxeter system.
When multiplied by, but if one length of S0 times something, just like we had.
Then it depends on something. So the statement is the affine vowel group is a Coxeter group. So every element can be written as a product of S0 and under some simple reflections. And then you take the minimal possible length of writing it in such a way that's the length of W. Yeah. Yeah, sure.
I think I didn't understand something here. So we get the first result, the length of this translation is M.
Yes.
So I'm the length of W at the other end.
Yes.
So then shouldn't both the sums be
No. Well, if W is empty, this condition we're always in this situation. Yeah. Okay. So just as in the finite case, still over there, the affine Hecke algebra, or rather this extended affine, so we also have an extended affine Hecke algebra. Whose presentation is just as follows. So this presentation, I will call it Coxeter presentation. So we will just go on by making Q a formal variable, and you can even work over Z. So this H extent is a ZQ plus minus 1 algebra with a basis given by TW, with W belongs to the extended affine vowel group. And then the relation is as before, so subjects to relations that you have TW times TV is equals to TWV if the length add up. So if L of WV is L of W plus L of V. And then you have the same thing for the simple reflection. Ts minus Q is equal to 0, but only that now you not only have this relation for the finite reflections, but for all the affine reflections.
Yeah, I have a question
Yeah.
about the length. So, is it the property of the length or the definition of the length?
This is the property of the length.
What is the definition?
The definition, yeah. So the definition of the length is you use you say this one is a Coxeter group, and you just use the definition of the Coxeter length for the Coxeter group. That is so for any Coxeter group you write W as
WX is not
no, and all these elements are length 0.
So we define the length of such an
Right.
as the length of its component.
Yes. Right. Okay. So you can take this as the definition of the affine Hecke algebra if you want. So maybe just to remark. First of all, you can easily observe by definition that the finite Hecke algebra is a sub-algebra inside the affine Hecke algebra, just by sending TW to TW. Where W belongs to WF. And moreover, since for any elements in omega, as we just discussed, so maybe x in omega, the length of x is 0, and so the Tx is always additive, and its inverse itself. So even at the level of affine Hecke algebra, so this extended affine Hecke algebra is equal to the affine Hecke algebra, where the notation explains itself, I hope. So this means this is algebra with basis in the affine vowel group, semi-direct product with this omega. Okay. Okay, and then of course, if you specialize Q to 1, you get back the group algebra of your extended affine vowel group. All right. So okay, let me do a board exercise. But as we have seen for the extended affine vowel group, this group not only has a Coxeter presentation, it also has a presentation as this finite vowel group times with this abelian part, is the lattice part. So you can ask in the so which one is this? You can ask in the affine Hecke algebra, can you find a similar presentation which is which is closer to this presentation of where you have a big commutative set algebra, which is this lattice group, and then you have a finite vowel group part. It actually exists, and then this is the so-called Bernstein presentation. So this is the next thing I want to discuss. So the idea is you want a big commutative subalgebra in this extended Hecke algebra, isomorphic to this. And you notice from this lemma that you cannot just take, so this lemma there tells you that if you just pick arbitrary, if you just take the elements corresponds to translation for a certain lambda 1 times translation for lambda 2, in general, this will not be equal to the translation of their sum in the Hecke algebra, because their length doesn't sum up. Okay. So you have to do something to correct this. The way you do this, well, the way Peng Shan does this, is the following. So simply, you for any lambda, you write it as so you write it as a difference of two dominant co-weights. So where gamma and gamma prime belongs to x check positive. This is all the elements such that when you pair with positive roots, this is positive. Okay. So this is always possible, and then you define an element x lambda. So I apologize for the notation, but I don't want to change it. So this x lambda will be an element in the affine group, and this bar x will be the lattice. So this element will be defined as T gamma times T gamma prime inverse T. Lots of T's. Okay. And so it's an exercise to show that this doesn't depend on how you decompose. So x lambda doesn't depend on the decomposition. T lambda is invertible. I didn't explain, I agree, but it is. So actually all the elements TW are invertible, as you can see from So this relation tells you that TS plus Q minus 1 times TS or minus is equal to Q, and therefore TS is invertible, and then you write TW as product of TS. Therefore, all the TWs are invertible. Yes.
Sorry, where do we define the affine?
Yes. So the affine Hecke algebra is the extended affine Hecke algebra, where you just replace the extended affine group by the affine group. That's the definition. Okay. So I think for time reasons, I will not explain this. If you want to know the proof, you can come to the exercise session and I can explain to you. So notice that x lambda is, I emphasize it's not t of t lambda, something else. But an important property of this x lambda is that if you take lambda mu two co-weights, then x lambda times x mu is actually equals to x plus mu. Okay? And therefore, they generate a subalgebra inside the affine Hecke algebra. So if you do all this x lambda, this is really isomorphic to Q inverse of x check as an algebra, and this is a big commutative algebra sits inside the extended affine Hecke algebra. Okay, so this is nice, and maybe let me write here. Just a good position. So using these elements, we can give another presentation for the affine Hecke algebra. This is due to Weinstein. So it says our extended affine Lie group, affine Hecke algebra, defined in this way, is also the ZQ inverse algebra. So generated by now TS for as a finite reflection, and x lambda with lambda belongs to x check, subject to the following relations. So first of all this TS generates a subalgebra which is isomorphic to the finite Hecke algebra. Okay. And second, well, as we already noticed, so x times x mu is equal to x lambda plus mu. And finally, I need to tell you how does TS commute with x lambda. And so for S, let's say S equals of S alpha check in a finite simple reflection, and lambda in x check. So if you do Tx times x lambda minus x lambda times Ts, this, S of lambda times Ts. So if we were in the case of group algebra, then we just have these two are equal. Okay, because in the group algebra, the finite Lie group acts by semi-direct product on the lattice part. But here there's a difference, and this difference is 1 minus q times a polynomial term. So this is x lambda minus x of s lambda quotient by 1 minus x of negative alpha check. Okay, and this is the presentation for the affine Hecke algebra. This is another presentation. So, any questions? I'm waiting for a question. So first of all, there is a remark. So you notice that if lambda is 0, then this is the identity elements in the Hecke algebra. And in particular, x of minus lambda is x lambda inverse. And second, so you need to observe why this is an element in the affine Hecke algebra. Okay, so what does this mean to quotient by this? So recall that if you do S alpha check of lambda this is lambda minus alpha lambda of alpha check, okay, where this is an integer. And so therefore our x as alpha check of lambda is x lambda times x minus alpha check to this power alpha lambda. Okay. And now you can interpret this difference like 1 minus x minus lambda check as x lambda times 1 minus. And this makes sense if you develop this. Okay? Okay. All right, maybe one more remark is that, as you can notice, well, maybe you need some work to notice that this elements tw times x lambda for w in the finite vowel group and lambda in this co-character lattice, they form a basis of this extended Hecke algebra. Okay. All right. Okay, my time is like up. Yeah, maybe I will just. Let's see. Yeah. I'll just give a description of the center, and then we'll leave the polynomial representation to next time. So, if it's negative, then you just put it on the other side. X are invertible, and then so you just. If it's negative, then you just write this as x alpha check, like alpha lambda times x alpha check negative. Minus 1 and then you develop it. So. Okay. So since like our extended affine vowel group is a semi-direct product, it's not hard to observe that the center of this group algebra, this is the same as, so you take this lattice part, the group algebra of this lattice part, and you have an action of W finite on this lattice, and you take the invariance. Okay. And it turns out the similar statement holds for the affine Hecke algebra. So this is again a theorem of Peng Shan, that the center, so center of the extended affine Hecke algebra is isomorphic to Q inverse times. So it's actually isomorphic to the same sub-algebra. Okay. I think I will skip the proof. Well, maybe just one key point of the proof is that for any lambda, you define an element z lambda, which is the sum of all the elements in its finite vowel group orbit times x lambda prime. And you first prove, just using relations, that this belongs to the center of the extended affine Hecke algebra. And then, well, a little bit more than just using the relations. And then you show that they span the center using the specialization map. From at q equals to 1. Okay, let's see here. Okay, there is some work, but it's not too difficult. Okay, I think I'll stop here. Thank you.
Questions?
Yes.
I have a question which has been already asked. I'm still confused about the definition of the length of the extended cycle.
Yes.
For the finite, you define this as a cardinality, using the cardinality, but for the extended, I don't think
You can also use incardinality. You can also use, let's say if k is it is also it is possible. So if let's say if k is just fq of t, I think it should work for any local field, but I'm more familiar with it. And you just take you take the cardinality of this. This is always finite dimensional, and this is also q to the same thing works. Yeah.
Is there any other question?
So you said it already, but can you say again, how do you define the affine Hecke algebra?
So, okay, so let's see, where did I define? So, all right. So the extended affine Hecke algebra is defined as the algebra with a basis with elements indexed by elements in the extended affine group and subject to these relations. And now the affine Hecke algebra, I guess I should write it on Word. So this is just the same thing, and here you replace it by belongs to the affine group. That's it. It is, as I said, so all this depends on your choice of the group. If G is simply connected, then you get affine Lau group. So where was it? So this thing is general. It depends on your choice of the group. Whether you choose simply connected or a joint or something in between, it will change the lattice. If you take simply connected, you get precisely the affine Hecke algebra. But if you take other group, you get some extended version of it. Yeah. It's a question about the co-characters in your group. Yeah. It will be something in between. Yes.
More questions? No. If there are no more questions, we thank the speaker again.